Okay, good morning. Welcome back. It's 11 o'clock. So before we start, please, you have any questions, any issues you want to talk about? Okay. So if there are no questions, then let's continue from where we left off the last time. I'm sharing my screen. If you can't see, do let me know. So the last time we met, we were looking at example 1, right? We are under session 3.8. Give me a sec. Okay. So we are looking at session 3.8, right? And we're looking at what do you call it? The exponential growth and decay, right? Exponential growth and decay. So we were looking at the first model, which is population growth, right? So we wrapped up. Let me go to example 1. Yeah, so this is where we are. So use the fact that the world population was 2560 million in 1950 and 3040 million in 1960 to model the population of the world in the second half of the 20th century. Assuming that the growth rate is proportional to the population size. So that's our cue that we have to be using the model that we talked about, right? P of t equal to P of 0 and then e to the kt, right? What is the relative growth rate? In other words, find k, and then use the model to estimate the world's population in 1993 and to predict the population in the year 2020, right? So let's get back to the whiteboard and work this problem. So we're given information about the population in 19. Okay. So we're given information about population in 1950. That was given to be 2560 million. Right. And then in 60, we have it to be 3040 million. Okay. So modeling this, our formula is given by P of t equal to P of 0 e to the kt, right? So for the first part, let's try and identify the parameters that we are given and then solve for the ones we don't have yet. Now for this standard model, what you usually solve for or be looking at to solve for is this one, which is the P of 0 and then the k, right? Which is called the relative growth rate under the population growth rate model, right? So for this one, we can set t to be equal to 0, right? So set t equal to 0 in 1950, right? Because that's the what do you call it? That's the latest time we're given. Like that's the earliest. The people are still coming in. So okay, so that's the time that we're given, right? The earliest time that we're given. That's in 1950, right? The earliest time that we're given. So we set that earliest time to be equal to 0, right? At that time, we have t equal to 0. So if you are told that in 1950 is 2560 million, right? Which is 2,560 million, then your P of 0 is equal to what? It's just simply 2560 million. Right. So now that you have that one, let's try and compute the key. Let's try and find the key. You're also given that in 1960 is 3040, right, million. So the thing is, if in 1950 we have t to be 0, then in 1960, what is t? Can anyone tell us what that is? If 1950 t is 0, then in 1960, what is t?
10.
10. Perfect. Thank you. Right? It's going to be 10 in 1960. So that what that is saying is P of 10 is just equal to what? Is that 3040 million, right? Now, all the values I'm going to write are in million, so I won't be repeating the million, right? So 3040 million, right? But in the same sense, we can plug just the 10 in the formula and get this 3040, right? So if you plug the 10 in there, repeat the P of 0. But P of 0 has already been found to be 2560 million, right? So just 2560, and then e to the what? K. K is something we don't have. And then what is t? T is 10 at that time, right? So we have this equation. Now, with this equation, we just have one unknown, right? It's just this one equation with one unknown. So that's 10k. So we just have to solve for k, right? So solving k, I think I see something in the chat. Oh yeah, perfect. Thank you. Yeah, thank you, Megan. Yeah, so that's true. Okay, so in solving for k, what do we do? The first step is we can divide both sides by the coefficient of the e, right? So that's divide both sides by 2560. And then that will leave us with e to the 10k equal to what? So that's just, I can simplify this a bit to 304 over 256, right? And then we take the natural log of both sides so that the power here can come down, right? Because remember that in logarithms, if you have ln of, say, e to the n, is just equal to n, right? So just take log of both sides. So ln of both sides. So e to the 10k. And then equal to what? Ln of that other side. So 304 over 256. And then when I get to this part, based on the property that I just talked about here, this part will just be 10 to the 10 times k. And then this side will be equal to what? Ln of 304 over 256. So solving for k, I'll just divide both sides by 10. I get k equal to 1 over 10 ln of 304 over 256. Right. And don't forget that this is the same as this is the relative growth rate that we were asked to compute. Please, any questions on this? Okay. Now, with this, the k obtained, that means that you now have a formula for the population at any time t, based on this model, right? So the population at any time t will just be, so you have 2560, and then e to the what? K. Now k is something we solve for. It's 1 over 10. And then, I mean, you can simplify this if you want. There are so many ways you can break this down, but simplification is not the goal here. When we get our answer, that's fine. We can just put it in there. So that one, and then times what? T. So this is your actual model. So now that means that whenever you want to find, now that you have the model at any time t, when you want to find a population at any time t, you just plug the t in there, and then you have your population estimate for that. So that's how that works. Please, any questions on this? Okay. Anybody needs time here? Maybe it's going to ask us some other questions. So I'll check the PowerPoint and then see. I think I see something. Will these be questions plugged in values? Or will they just be used to make the model? Oh, okay. Will there be questions plugging values into that? Yeah. So there's likely to be questions. That's why I said, let me check the PowerPoint. It's likely that now that we have the model, they will ask us to estimate the population at some time, right? So if they ask us to estimate the population in, say, 2021 or something, then we just have to figure out the t and then plug it in the model and get our answer, right? So let me check the PowerPoint. Okay, so on the PowerPoint, let me share this. So back to the PowerPoint, you can see that. So back to the PowerPoint, you can see that the question says, okay, so what is the relative growth rate? So that's the key. We've solved that. It says use the model. You see, now we have the model. Use the model to estimate the world population in 1993 and to predict the population in the year 2020, right? So let's do that. 1993, 2020. So let me go back here. So in 1993, the question is, what is our T? Can anyone help us with that? If T is 0 in 1950, in 1983, what is T? Okay, give me a sec. Yes, that's true. No, close, very close, Megan. Don't forget that T is 0 in 1950. I don't know whether it's a typo, but very close. In 1950. Anybody wants to try? What do you think? Oh, yeah. Yeah, so the base here is 1950. Perfect. Yeah, so it's just going to be, T is going to be what? So 1950 and then 1983. So that'll be just 1993 minus the base year, which is 1950. So that would be equal to 43, right? So all that you need to do is, since you have the model for the population at any time t, you just find P of 43, and that'll just give you, so we have 2560, right, in e to the what, k. So that'll be 1/10. Okay, let's do 43 over 10 like so, and then ln of 304 over 256. I hope I got it right. Yeah, 30425. Oh, yeah, and then t. Yeah, so that's it. And then with this one, you just plug it in your calculator and you get your estimate. Let me just pick the value from here. Now, since this one, you have to use a calculator to compute some of these values. I will not be testing you on this on the exam, right? On the exam. So that one is approximately 5360 million. So that's 5360 million. Million. And that's our answer. But on the homework too, please make sure you check out what the question is, how many decimal places the question is asking you to put it. If it says put in the exact value, then you have to type this in. But if it says you can estimate you can round to some decimal place, then you put in. So you put in how it wants it in, like the format. So that's just by the way. Please, any questions on this? Okay, now what about in 2020? So in 2020, we will compute it similar to what we did in the 1993, right? So for 2020, let's check the time. So that will just be 2020 minus the base year, which is 1950. And what is that? So T will be equal to what? Yeah, so I mean, 50 years is just going to be
70.
So 70, perfect. Thank you. So T equal to 70. So that means that you just need P of 70, and that'll just be equal to 2560 e to the what? 70 over 10 ln of what? 304 over 256, right? And then depending on what the question asks you to approximate it to, for this one, we just approximate to the nearest thousands or some thousands of millions. So that's 8524. So 8524. Approximately 8524 million. And that's all. We are done. Please, any questions here? Okay. Anybody needs time here? Okay, then let's go back to the PowerPoint. Okay, so the graph that you see here is just illustrating the true population and then the model that we have, right? The red is a model. The red line is a model, right? And then the blue points are the population, the exact populations at that time. And you can see that this model is doing fairly well, right? It's doing very well, fairly well. Looking at, it's very quite close to the points, the blue points, right? It's very, very close. But one thing with prediction is the farther away you are from the point that you are predicting from, the more prone the model is to errors. For example, it's likely I could predict where you will be in the next 10 minutes than say in the next 10 years, right? Do you see? So if I create a model around it, the 10 years model will it's likely it may predict wrongly than the one that predicts close to the future. So that's one thing about model building. You see, that's why it says prediction in 2020 is riskier. That's what it means by this. Okay, please, any questions here? Okay, so if there are no questions, that's it for population growth, right? Let's get to radioactive decay. Now, unlike the population growth, whereby we're expecting an increase, for radioactive decay, we have a substance which is emitting radiation and hence is shrinking in size. So it's decreasing, right? So the model is still the same, but there are just a little bit of differences in some sense, right? Like we will not be dealing with P again, we'll just be dealing with M. And then in this case too, we have a K being a constant, but then the K is negative, unlike the population where the K is positive, right? The K is negative. So that tells you that it's a decay. Okay, so now the model still is just the same structure, right? So you have the mass at any time t equal to what? The initial mass and then e to the kt, right? Now we are going to introduce a new term under radioactive decay, which we call half-life. Now, half-life is the time required for half of any given quantity to decay, right? So there are two ways of looking at it, like either a glass is half full or half empty, right? In the sense that you can say half-life is also the time that half of the substance will be left. You see, either half is left or half is decay. Yeah, so that's half-life. So this term will come in, it will come to play. It will help you to solve for some of the parameters at some point. Yeah, but that's all there is to this. Please, any questions on this, on the concept? Okay, then let's get to example 2. So for example 2, we have radioactive decay. Example 2. On slide. Okay, so let's gather some information from that question. So it says the half-life of radium-226 is 1,590 years, right? And then a sample of this substance has a mass of 100 milligrams. Find a formula for the mass of the substance that remains after t years. So it's kind of like find the m of t. You see, find the formula m of t. And then the B says find the mass after 1,000 years, correct to the nearest milligram. And then C says, when will the mass be reduced to 30 milligrams? Okay, so let's do this. Now, the information that we are given here is half-life of radium-226. Right? Radium-226 is 1,590 years. So let's employ that idea. So half-life. Of radium-226 is 1,590 years. So our model is given by m of t equal to m of 0 and then e to the kt, right? So if you are told that the half-life is 1,590, what that means is half, so m of 590 will be equal to what? Half the initial mass, right? So at that time, the original mass that we started was m of 0. Let me use the similar notation. This has to m of 0. It's still the same thing though, right? So the original thing we started with was that large. It was m of 0 large. So in 1,590 years, we expect half of it to be remaining. So that means just half of what? M naught, right? Or m of 0. Now, this thing here is the half-life interpretation, right? Half-life. But then we have a formula for getting the mass at any time t. So just as we have the half-life giving us m of 1,590 to be equal to half of m0, we could have just found m of 1,590 to be equal to what? M of 0 e to the what? K, t is what? 590. So this same m of 1590 is half m of 0, and this same thing is what? M of 0 e to the k 1580. So since the two are supposed to be equal, you can just set them to be equal to each other. So you have this equal to what? M of 0 and then e to the what? K 1590, like so. And then when you get here, you just solve for the k, right? So what I see here is I can cancel out the initial mass, right? So these will cancel out. And then that will leave me with half equal to what? E to the what? 1590k. And then at this point, I just try to solve what the k. How will I do that? Well, to see what I'm going to do, I will need to move on to the next slide. So please do let me know if you need more time here. Okay, so moving on, that means we have half, let me rewrite it, half e to the 1590k. Let me see if I got this right. Yeah, that's true. Okay, so to solve for the k, first take the natural log of both sides, right? So you do ln of e to the 1590k. And then this is still ln of 1/2, and then this equal to, now if you take ln of e to the power, it's just that power, so 1590k. And then at this point, to solve for k, just divide both sides by 1590. So you end up with k equal to what? You can do 1/1590 ln of 1/2. Yeah, and then you're done. So that's your k. But now that I have my k, right, I can use this to get my, oh, okay. So we are also giving, in part A, we're also giving the initial mass to be 100 milligrams, right? So I can use this 100 milligrams together with the M of 0 to get the M of T, right? To get the M of T. But by the way, let me number this as A, this part A, right? So together with this, so the M of 0 and then the K will come together to give me the mass at any time T. So that's M of 0, so that's 100. E to the K, what's K? 1 over 1590, ln of 1 over 2, and then times T, so like so. And as I said, you can also simplify this in another way, right? You can simplify this if you want, but simplification is not the goal. This is okay. This will do just fine. Okay, please, any questions here? Is this the same as, let me see, is 1 over this the same as, okay, so a question, let me see. So you're saying is 1 over 1590 ln of 1 over 2 the same as ln of 1 over 2 times 1, okay. Do you mean times 1 over, okay. Like so? Do you mean like this? Okay, no, they are different. They are different in the sense that, let me try and simplify and show you. For the first one, you can take this to the power. So it's possible you can rewrite this as ln of 1 over 2 to the what? 1 over 1590, right? Is this. And then the other one is the same as, it's kind of like ln of 1 over 2 times, no. So you can, since it's product, you can just plus, so ln of 1 over 1590. So these are two different things. You see? Yeah, these are two different things. For this one, you're adding this and this. For this one, you're taking an exponent. So they are not the same. Are you okay? Okay, you're welcome. Okay, so now let's move on. So that's part A. Now let's move on to part B. Share screen. Okay, so for part B, it says find the mass after 1,000 years, right? After 1,000 years, correct to the nearest milligram. So after 1,000 years, we know that the time is 1,000. So B, T is 1,000. So all the question is asking for is when T is 1,000, right? What is the mass at that time? So we are just directly finding M of 1,000. So that just be 100 E to the, I can move the T in front. So I get 1,000 over 1590 and then ln of 1 over 2, like so. And then that'll give us an estimate. It says round to the nearest milligram. So let me look at the answer and just write it there, 65 milligrams, approximately 65 milligrams. Right, so that's it, we are done. Now the C says, the question C says, oh, come on. Yeah, when will the mass be reduced to 30 milligrams? So for that question, it says that there is a certain time when the mass is what? 30 milligrams. So that means that for this one, the information that we are giving here is M of T. So M of T is 30. What is that T? Right? What is that T where the M of T is 30? So let's do that. So we know M of T at some times is 30 milligrams. It's 30 milligrams. And then we have a formula for the M of T. So it's just 100 E to the what? I can just put a T here to simplify things a bit. And then ln of 1 over 2 equal to what? 30. So that's what this means. So for this one, when we set this equation, we just solve for the T, right? Okay, so the first thing I can do here is just divide both sides by 100, right? So I'll get 0.3 on this side, and then the hundreds will cancel out here. Now to continue, I have to move on to the next slide, but do let me know if you need more time. Yeah. Okay, so if you don't need time, then let's move on. So that means that we have E to the, what's left here? T over 1590. Then ln of 1 over 2. Yep, and then equal to 0.3. Now, when you get here, in order to find what is in the power here, you have to take ln of both sides. So ln of this result, and then equal to ln of 0.3. And then for ln of e to some power, it's always going to be that power. So just t over 159, t over 1590, ln of 1/2 equal to, and then this one is still ln of 0.3. And then when you get here to solve for t, I will multiply both sides by 1590 and divide both sides by ln of half. So that give me t equal to what? 1590 ln of 0.3 all over ln of what? Half. And that's my answer. So looking at the approximation, let me get the approximation. That time is 2762. So t is approximately 2762 years. Okay, and that's all on this. Please, any questions here? Anybody needs time here? Okay, then let me share the PowerPoint. Okay, so the PowerPoint just has this thing written down, like nice notes for us on this problem, right? So yeah, but if you have any questions or you don't understand anything, let me know. Like, is the process okay? Is the procedure fine? Do you have any issues? Okay. Then let's move on to, okay, I think I see something. Give me a sec, chat. Oh, okay, wait, yeah, okay. Do you want me to wait on this slide, on a previous slide, or how do you get 65 milligrams in example? Okay, like the math part. Oh, okay. So let me go back to the whiteboard. How I got the 65 milligrams. So let me go back. Okay, so this is here. So I hope you understand how we obtain the formula for m of t. You get that part. You get this one. How you set that equation, but okay. Yeah, so for the B, right, it's asking us what is the mass at 1,000 years, right? What's the mass remaining at 1,000 years? So that means that the T is 1,000. So I'm just plugging the 1,000 in the formula that I obtained. Don't forget that the formula is the mass at any time T, right? So M of 1,000 is just wherever you see the T there, put the 1,000 there, right? So I just did it like 100 e to the what? 1 over 1590 ln of half and then times t, but it's the same as t over 1590. So I just put 1,000 in the formula. And then when you get here, you just plug it in your calculator and then you get your answer. Please, does that make sense? Or still? If it doesn't make sense, maybe we don't have calculators. Yeah, that's what I'm saying. I'm not going to test you to calculate something like this on an exam, right? I'm not going to test you to calculate this, to approximate and round and stuff. Yeah, so chill. No questions on that. Yeah, you're welcome. Okay, so now let's move on to the other part. So we are done with radioactive decay. The last part we're going to check is continuously compounded interest. And then for this, let's look at an investment, right? So if we have $1,000 and we want to invest at an interest rate, 6%, and it's compounded annually, then after 1 year, the investment is worth this. So this is how much you expect to have in your account after a year. Now, what you're going to have is, if it's 6% interest, it's just 1 plus the interest times the principal, right? So this money that you deposit in there is called a principal. And then you have the interest rate. So compounded annually, right? So that means after every year, right, you get this amount, right? So for this 1,000 times 1.06, that's 1060. Now, if you're still interested in earning at the same interest rate, you can just put this money back in there and then you earn this. Or suppose you don't go every year to get it and put it back in, and you invest it for say 2 years straight. Then that means that after the year, when you get the $60 on top of the 1,000, then the $60 is also going to earn interest as well as the what? The $1,000. So the interest earns interest, and then the original principal also keeps earning interest. So at the end of a year, you have this amount. So everything just resets. It's almost as if you have a principal 1,060 invested, right? So that 1,060, when you invest it, it's just this over another year, it's just that amount times what 1.06 again, right? So in general, if you're investing that 1,000 for T years, at an interest rate of 6%, then the formula is just 1,000 and times what 1.06 to the T, right? It's just 1,000, 1.06 to the T. Okay, now, when you invested at this amount, so this one is for just the example that I gave. So let's suppose that A naught is the amount invested, right? And then the interest rate is R, right? Then that means that the formula for the accumulated amount at any time T, say you want to invest this A naught at for T years and at a rate of R, then that means that the amount that you should expect is what? A naught and then times what? 1 plus R to the T. Now, yearly compounding is sometimes you can earn more if you get like more compounding within a year, right? So for a year, you don't have to wait for a year. You can have your interest, you can have your investment compounded or compounding interest for time interval shorter than a year, right? So that's what this is saying, that usually, however, interest is compounded more frequently, say n times a year. So let's see why people want their money to earn interest at a faster compounding interest, right? At a faster compounding period. So for this one, we have this formula. If you have a rate R, and then you are compounding, say, n times a year, right? Then that means that your formula is given by A of 0. So A of 0 is the principal, and then times what? 1 plus R to the n, all to the n times T, right? So for instance, if you're still looking at the money that we are talking about, the $1,000 invested at what 6% interest. So it's the same preamble, right? $1,000 invested at 6%. Then if you compound much more frequently, like say annual compounding, we know that this one is 1191.02. So this is for 3 years, right? So if you invest this for 3 years, then you're getting this amount at the end of the 3 years. Now, suppose you want to compound it much more frequently, say twice a year, right? If you are compounding it frequently, like twice a year, it's called semi-annual compounding. And for that one, the formula is given by this, what you see here, A of 0, this is the formula, right? So for this one, how you are getting this is just 1,000 and then 1 plus what? 0.06, right? That's the rate. And then the N is what? The N is 2, right? Because you are compounding semi-annually, twice a year. And then all to the power what? N times T. What is N? N is 2. And then what is the time? The time is 3 years, right? So that's how come they are getting the 1,000 and then 1.06 divided by 2 is 0.03. So that'll give you 1.03 and then all to the 2 times 3 is 6. So that's how they are getting this formula, right? So everything is from here, right? Okay. So that's semi-annual compounding. Now look at what happens when we compound much more frequently. Now for the annual compounding, if you compound it annually, you're getting 1,191 and then 2 cents. But if you compound semi-annually, look at the amount you're getting. You're getting 1,194.05. Now someone will say this difference is not too much. It's like $3.03. But think about investing like, let's say hundreds of thousands of dollars or like millions of dollars. Then this is going to be pretty significant. You see? So that means overall, people will like it if they get much more compounding within a year. So semi-annually is 2. Maybe you can do better, right? We can do more. We can do quarterly compounding. So for quarterly compounding, that means you're compounding what? 4 times a year, right? For 4 times a year. So the formula is still the same, right? You're using this formula. So for quarterly compounding, how are they getting this? Well, they are getting this from 1,000, which is the principal, 1 plus what the rate is 0.06 over what? N. What is N? When you compound quarterly, then your N is what? Is 4. And then all to the power 4 times what? What's the time? 3. So this will give you 0.06 divided by 4 is going to be that 0.015. So that's 1 plus that will give you 1.015. And then 4 times 3 is 12. So that's how come they are getting this, right? But we can still do more. We can do better, right? So someone will say, oh, since you are computing frequently, my money is going up. Maybe I want much more, right? Can you give me more? Then they will say, okay, what about monthly compounding? And we are all excited about monthly compounding because that one you'll be getting more than the quarterly, right? So for that one too, what do you get? when you do that one, your N is what? It's 12 because you're compounding it 12 times a year. 12 times a year, right? So that one too, it will follow the same formula. The N is 12, and then you get this. But look at the values. You see that anytime you compound it much more frequently, the amount of money will earn more, right? There'll be much more money at the end of the term of the investment. So someone can take it further. Okay, so investment company, what can you do for me? Can you do it better? I want more money from this investment. It was okay, fine. We give you daily compounding. So okay, yeah, daily compounding is better than monthly because that one you'll be compounding it 365 times, right? So approximately 365 times. So using the 365, right, it's still the same thing. It's still this formula. The N is 365 times a year, and then the rate is the same. But as you can see, the amount is still a bit higher than all the others. So someone will say, okay, another customer will say, okay, well, I can see that the much more frequently you compound this, the more money I'm getting. So what's the best case scenario you can give me? What's the best you can do for me? What's the best case scenario? They'll say, okay, what about we compound it continuously, right? So compounding it continuously is like the number of times that you're compounding this one is infinite. You see, it's infinite. So that means that the best case for this compounding is just breaking this the number of times you are compounding this within a year to be what? Infinity, right? Because the much more frequently you compound it, the much more money you are earning, right? So that one is what we let N approach infinity. That's for the continuously compounding, right? So when you hear continuously compounding, we are letting the N approach infinity. So we are still using the same formula, which is what you have here, right? So the accumulated value, this is the value in the investment at time t. That's the A of t. It's just going to be what? A of 0, 1 plus R over N, all to the NT. But for this one, we are letting the N approach infinity. So you see, even with finance, you see this calculus come to play here. It's just a limit, a limiting value. So the limit as the N approaches infinity of that formula, A of 0, 1 plus R over N to the N to the T. Right, so let's see where this formula leads. Now, the first thing you can see here is A of 0 is a constant. So by the constant multiple rule, you can pull it out, right here, right? You can just pull this one out right here to wait. Okay, and then let's look at this one. Now for this one, for the other piece, for the second piece, I think I need to, let me work this one. Let's derive this. Continuously compounding interest. Okay, so we know for that one, we have A of t, the accumulated value, to be limit as N approaches infinity of A of 0, then there's 1 plus R over N times t. Okay, so now let's do this. So for the first one, we have A of 0 to be a constant. You can pull it out. And then you have limit as N approaches infinity. And then I have 1 plus R over N and then N to the T. Right. But when I get here, let's see what I can do here. Well, I can just do some manipulations here. I can have this to be 1 plus 1 over N over R. And then this is also the same as N over R, and then times what? R times T. Please, are you okay with this manipulation, right? If I have R over N, it's the same as 1 over N over R. And then if I have N times T, it's the same as N over R times RT, right? Because I've not done anything because the R can cancel out and I have NT back. And then for this one, 1 divided by N over R is the same as R over N. Please, are you okay here? Okay. Now, the thing is, suppose I let M equal to N over R. If I let N equal to N over R, I want to change the limit from N to M, right? N to M. Now, if I let M equal to N over R, then as N approaches infinity, N over M will also be approaching infinity because it will be N over R. Don't forget that the rate of interest is always a positive. No one invests money for it to decrease. right? Unless maybe you're investing in stocks and you expect maybe the returns could go negative. But when you're investing your money, you expect what? The rate to be what? To be positive. So that's why infinity over positive is infinity, right? So when the n approaches infinity, m will also be approaching infinity. Now, using that trick, let's see what we are getting. We have a of 0, and then the limit, what? N approaching infinity is just m approaching infinity. And then I have 1 plus what? 1 over what? N over r is m. And then m. And then all to the power r times t. But then when you're doing the limit of a function to a power, you can take the limit of the base and then take the power, right? You can take the limit of the base and then you, after obtaining your answer, you take the power, right? So that means that this thing, anybody needs time here? This thing becomes a of t becomes a of 0 equal to, not equal to, a of 0. And then I have limits as m approaches infinity, and then 1 plus 1 over m to the m, or to the r times t. But my question is, what is this? Does anyone remember what this is? I told you I'll be using it at some point. Now it just came up. Does anyone know what this is? Anybody? What is this? Do you remember? Close. I have infinity. Close. Can you try? We did this not long ago. Do you remember what that is? Anybody? It's E. Do you remember E as a limit? This is E, right? So that means it becomes what? A of t equal to A naught, E to the RT. Now, this is the formula for continuously compounded interest. Now, this model is just similar to what we had for the previous models, for population, and then for what? For radioactive decay, right? You have the initial amount, the future amount is what? The initial amount, and then E to the what? The K. The K is now R, and then times T, you see. So that's the formula. So whenever you hear of continuously compounded interest, you're just referring to what? This formula, and that's all. Right. So back to the question of the investor who wants the best possible case, right? If you're going to compound it continuously, then what you have to do is just going to be 1,000 e to the what? 0.06 times the time, right? So that's all this is saying. Please, anybody needs time here? I'll need to conclude on a PowerPoint. Okay. So let me go back. So for continuously compounding, following the proof, right? This limit is just E, right? So that means that we get this formula. And it's just the same model that you saw. The rate of change of the investment is just R times what? A times T, right? This same differential equation, right? So for the investor who wants this $1,000 for 3 years compounded what? Continuously, this is the formula that we're going to use. So just 1,000 e to the what? The rate, 0.06 times 3. And that's 1197.22. Now you can see that this amount is very, very close to the daily compounding, right? Compounding daily. And that is expected, right? But at least you get like 2 cents off. But as I said, don't look at it in terms of these small numbers. Think of investing very, very large sums. For those ones, these will be very important. How frequently you get your investment you compounded is quite important, right? Yeah, so that's it on this. And that's all on 3.8. Any questions here? So plug in the values will be on an exam. Yeah. So I'll be asking you to plug in values for this one because you need a calculator, right? Okay. Please, any questions on 3.8? Okay, then let's move on to 3.9. Okay, I'm sharing a screen for 3.9. If you can't see, do let me know. Now 3.9 is related rates, right? So for related rates, we are interested in the rate of change of a quantity with respect to time, right? So let's look at this case, right? The example that is illustrated here. Say we are blowing air into a balloon. Now you see, when you blow air into a balloon, then you notice that the volume of the balloon is increasing with respect to time. So you are blowing the air into the balloon, right? With respect to time. Then you notice that the volume is increasing with respect to time. Okay. Now, at the same time that the volume of this balloon is increasing, its radius, the radius of the balloon is also increasing. But when it stretches, the volume is increasing, and then the radius of the balloon is also increasing, right? But it's easier to measure the volume of the balloon at any time t than to measure the radius of the balloon, right? So for this case that I talked about, the rate of change of the volume of the balloon with respect to time is easier. You can measure that one directly, right? Rather than the rate of increase of the radius of the balloon. So this is a problem which related rate solves, right? In a sense that you relate the rates. So you relate the rates that you know, and then ones that you don't know, and then use the one that you know to figure out the rates that you don't know, right? So for this one, say we're interested in finding an idea of what the rate of change of the radius with respect to time. Then all that we need to know is what is the rate of change of the volume with respect to time, and then we can figure out the rate of change of the radius with respect to time, right? Okay, so now that's the idea. That's the whole idea. So to see this, let's see this example, how this works. So for example 1, it says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeter cube per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Now, for related rate problems, they are story problems most of the time. So you just have to be able to pick out your information, right? Check what is given you, and then ask yourself what you are being asked to solve. So looking at this question and what we have here, we are told the volume is increasing at a rate of what? 100 centimeter cube per second. So if we let V equal to the volume, now this volume is increasing with respect to time. So that means that and then we let T be equal to time. T be equal to time. Then that means that 100 centimeter cube per second is just dV over dt. Right? So that's an information we get from there. Now the next part says, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? So how fast is the radius of the balloon increasing? So if I let my R be equal to the radius, can anyone tell me what I'm being asked to find here? What am I being asked to find? How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Anybody? What is that? What is the question asking for? Feel free to try. What do you think? Okay. I see something in the chat. Yes, it's a rate of change. But then if my R is radius, then what am I asked to find? Just as I have dV over dt to be 100 centimeter cube, what am I asked to find? Yeah, so it's true. It's a rate of change that we are trying to find. But which one? What are we trying to find? Yes, close, time, close. Half-life, close, still close. Is the R over dt? That's what I am asking. Is the R over dt the rate of change of radius with respect to time? So you all gave me pieces of the answer. Yeah, so technically you are all right together, right? Okay, so that's what we are asked to find. Now, how do you do this? Now, the first thing you just have to do is find an equation that relates the volume and then what you're trying to find, right? So the substance is a sphere. The substance is a sphere. Okay, it's 11:49, almost time. Okay, let me end here. I'll continue on this example on Monday. And please don't forget that the exam is on Friday. I posted the study guide already, right? So please look through as soon as possible and let me know if you are having any difficulty solving them. Yeah, thank you for your time. Have a good weekend. See you on Monday. Yeah.
Thank you.
You're welcome. Oh, Donovan, let me let me help you figure it out, like where the study guide is. I'll show you briefly. Give me a sec. So just go to, you're welcome. So just go to, let me first get out of this and save my file so that I don't lose them. Okay. Escape. Where's that? Okay, so okay, so when you come to files, right? I think they have student view somewhere. Student view. Yeah, so that's how you see it, right? So just go to files and then you scroll down. You see this exam 1 stuff. Okay, so exam 2 study guide is right here. You see exam 2 study guide. So you have it here. Yeah, so these are the questions. And then I have some solutions at the end, but maybe I might try and solve like detailed solutions for you guys. Yeah, but all the study guides are here for the final, even exam 3, exam the final. Yeah, so that's it. I'm on the files and there's only exam 1. Oh, really? Oh, okay, only exam 1. Okay, let me check again. I wonder why I can see it when I use the student view, but you can't. Okay, let me check. If not, then I'll have to check at your end. See, maybe let you share your screen. Okay, give me a sec. Stop recording.